Hello everyone, and welcome back. Today we're going to continue our exploration of applications of eigenvalues and eigenvectors. Last time, we introduced a theorem and it said this. If A, which is an n by n square matrix, has n independent eigenvectors, not necessarily eigenvalues, because they could have, for example, a full set of eigenvectors, but not necessarily true if they have repeated eigenvalues, then n has what we call an eigenvalue decomposition. A is equal to u to u inverse. In particular, A is similar to a diagonal matrix. So what's so special about this U? Well, U is going to be the columns are the eigenvectors of A, and this D is a diagonal matrix of eigenvalues of A. Of course, presented in the normal order. Now, there is a very important theorem that you need to know in case you don't already know, but all diagonalizations of matrices, if they exist, are eigenvalue decompositions. So when we first introduced the idea of diagonalizations, we were like, okay, A is equal to S ds inverse, right? So let's assume that we can diagonalize a matrix A, where S is some invertible matrix. Well, one can show that all diagonalizations of matrices are indeed eigenvalue decompositions. That is, it's sufficient and also necessary that D contains the eigenvalues of A, and S will contain the eigenvectors of A in the same exact order as presented on the diagonal entries of D. And of course, that's not unique up to scalar multiples of the eigenvectors and permutations on the diagonal matrix D. Right? So let's assume that A does have a eigenvalue decomposition. Does it allow us to do, for example, powers and inverses and things of that sort very, very easily? The answer is yes. So let's assume, and we're going to make this assumption for all of the things that we're building today. So suppose A has an eigenvalue decomposition. And one can ask, well, what if it doesn't? Can I still do these things? Yes, but not in the same way, which we'll talk about later. So what is A squared going to be equal to? So A squared is going to be equal to U d U inverse times U d U inverse. So we know already that matrix multiplication is associative, so we can rewrite this as U d U inverse by associating U inverse with U. So notice here that that's going to cancel into the identity. So we have that A squared is just going to be equal to U d squared U inverse. Keep in mind D is a square matrix, so this D squared is defined as usual. So notice what we have here. Keep in mind U is the eigenvectors of A and D is the eigenvalues of A. Notice that D squared is going to be the eigenvalues of A squared and U is going to be the eigenvectors of A. So there was a theorem that we proved some time ago. If lambda is an eigenvalue of A, then lambda squared is an eigenvalue of A squared with the same eigenvectors. And from this representation, it's actually quite clear to see that that is indeed the case. Well, what if I want to do, for example, A cubed and A4 and A5? Well, technically we can extend this via mathematical induction. So if we take k to be in the set of natural numbers, we have a to the power of k is going to be equal to u d to the power of k u inverse. Right, so we're just going to be exponentiating those elements on the diagonal of d. So d to the k is just going to be equal to d1 to the power of k, d to the power of k, all the way down to dn to the power of k, where those dj's are going to be the eigenvalues of your matrix. So let's look at a 3x3 matrix just to see if we can do some fun math. So recall the matrix 1, 0, 1, 0, 1, 1, and 1, 1, 0. We actually found the eigenvalue decomposition of this before. This was equal to 1 minus 1, 1, 1, 1, 1, 1, 0, minus 2, 2, 0, 0, 0, 1, 0, and 0, 0, minus 1, times the inverse of that matrix, which we could find if we really wanted to. right? So let's ask the question, suppose you want to find 101, 011, 110 to the power of 9. Obviously, you're not going to individually raise each of those elements to the power of 9. You won't get the same answer, else it's just the original matrix. So via this, we can actually have a shortcut. So this is going to be equal to 1 minus 1, 1, 1, 1, 1, 1, 0 minus 2. It has the same exact eigenvectors. But this is going to be equal to 2 to the power of 9, 1 to the power of 9, and negative 1 to the power of 9. So it's going to be equal to 512, 1, and negative 1 on the diagonal entries, and the rest of the eigenvalue decomposition is the same. So if you have the eigenvalue decomposition of a particular matrix, you can have the eigenvalue decomposition of any power for that matrix regardless of the order. So let's look at another question, because you can of course change this 9 to any number. So let's make this a little bit more fun. So how about e to the power of a, where a is just some square matrix? So how would we exactly find this? So if you remember from single variable calculus, the Taylor series for e to the x, where x is a real number, this is going to be equal to the infinite series, the sum from k is equal to 0 to infinity, of x to the power of k divided by k factorial. And in case you don't know what k factorial is going to be equal to k times k minus 1 times k minus 2 all the way down to 1, with 0 factorial defined to be equal to 1. So if we were to replace x with a matrix, then we have that e to the power of a can be defined as the sum from k is equal to 0 to infinity of a to the power of k divided by k factorial. And as long as a is a square matrix, a to the power of k is well defined. So no need to be diagonalizable even in that case. But if A does have an eigenvalue decomposition, in particular u inverse, then we have that e to the power of A is going to be equal to the sum from k is equal to 0 to infinity of u inverse to the power of k all over k factorial, which we already know is going to be the sum from k is equal to 0 to infinity of u inverse divided by k factorial. Notice that u and u inverse do not depend on k, so I can factor that out of the left and the right and write this as u times the matrix, the sum from k is equal to 0 to infinity of d to the k all over k factorial times u inverse on the right hand side, which is just the definition of u e to the d u inverse. U e to the power of d times u inverse. And here, e to the a was just e to an arbitrary matrix. Here, e is to the power of a diagonalizable matrix. So let's look at that e to the power of d in a little bit more detail. So e to the power of d, again, is just the sum from k is equal to 0 to infinity of d to the power of k all over k factorial. So what does this matrix d to the k over k factorial look like? So let's write that in matrix notation. So that's going to be d to the 1 to the k all over k factorial, d to the 2 to the k over k factorial, all the way down to dn to the k all over k factorial, 0 elsewhere. So if I add a bunch of diagonal matrices, that's of course going to be a diagonal matrix, and of course we're going to be adding up all those entries along each of those entries. So notice that that's just actually going to become e to the d1, e to the d2, all the way down to e to the dn, and of course that's going to be a diagonal matrix. So if that is going to be the result, that means we can find the eigenvalue decomposition of all of the diagonalizable matrices, and then find the exponential of those matrices just by exponentiating the diagonal entries in the diagonal matrix D. So to illustrate, let's look at a nice little matrix A, 4, minus 3, minus 1, and 2. So the first thing that we need to do in order to find e to the power of a is to find the eigenvalue decomposition of it if it has one. So one should be able to show that the eigenvalues lambda 1 is going to be equal to 5 and lambda 2 eigenvalue is going to be equal to 5. And of course there's going to be infinitely many eigenvectors, but you can choose one of them, whichever one makes you the most happiest. So one eigenvector for lambda 1 is going to be equal to 1, 1, and one eigenvector for lambda is equal to 5 is going to be minus 3, 1. So once you have that, then we can find the eigenvalue decomposition of A. So A is going to be equal to 1, 1, minus 3, 1. And then we're going to have 1, 0, 0, 5. And then we're going to have the inverse of that matrix A, which is going to be equal to 1/4 times 1, 3, minus 1, 1. All right, so that's the inverse of A, that's A, and that's going to be equal to D. So what is going to be e to the power of A? So e to the power of A is going to be equal to, so it's going to have the same exact eigenvectors, so 1, 1, minus 3, 1. And then we're going to have e to the power of 1, 0, 0, e to the power of 5. And then we're still going to have this 1/4, 1, 3, minus 1, 1, because it has the same exact eigenvectors. And once you multiply these three matrices together, you're going to have the approximated value 111.99, negative 109.27, negative 36.42, and 39.14, and that's the exponential of the matrix A. Right? Now, again, what if A was not diagonalizable? Then we can't do this. Then we, of course, get into some bigger issues. But keep in mind, all symmetric matrices are diagonalizable. So without question, if I give you a symmetric matrix, you should be able to find the eigenvalue decomposition of it, and moreover, any power, and also the exponential of that particular matrix. So let's look at a particular example just to illustrate that. So example. Suppose we have the matrix B, which is equal to 2, 1, 1, minus 2, which is indeed an symmetric matrix. So we're going to have not so pretty eigenvalues, but lambda 1 is going to be equal to the square root of 5, and lambda 2 is going to be equal to the square root of negative square root of 5. So some eigenvectors just for fun. Now these are not going to be the prettiest, but you can find them. That's going to be equal to 2 plus the square root of 5, 1, and this is going to be the conjugate of that, 2 minus the square root of 5, 1. So those are our two eigenvectors. So what is going to be e to the power of b? So e to the power of b, or the exponential of that matrix, is going to be, so we're going to have our eigenvector matrix, so 2 plus the square root of 5, 1, 2 minus the square root of 5, 1. Then our eigenvalues, square root of 5, e to the power of that, 0, 0, and then e to the power negative square root of 5. And then the inverse of that matrix, 2 plus the square root of 5, 1, 2 minus the square root of 5, 1, the inverse of that. And once you find the inverse of that matrix, not quite the most beautiful thing, e to the root 5, e to the minus root 5, and then that matrix all multiplied together, you're going to have the matrix 8.87, 2.07, 2.07, and 0.60. Now, one important thing to notice that this matrix is also symmetric. And one can ask, is that by chance? And of course the answer is no. Right? Let's look at just one other example, also for fun. Let's assume that we have C, 0, minus 5, 5, and 0. So we have an anti-symmetric matrix, or in particular a skew symmetric matrix, as some people say. Skew symmetric, anti-symmetric, same meaning at least from my experience. So our eigenvalues are going to be equal to plus or minus 5i, complex eigenvalues, but that's not a big deal. So lambda 1, let's say, is going to be 5i. Lambda 2 is going to be equal to minus 5i. And we're going to have some eigenvectors, v1 and v2, which is going to come out to up to scalar multiples, i1, and its conjugate, minus i1. So what would be the exponential of this matrix C? So e to the c is going to be equal to, so we're going to have our eigenvectors, i1 minus i1, and our eigenvalues, 5i, 0, 0, minus 5i, but then we need to exponentiate them, don't forget that. And then we're going to have the inverse of that matrix, I minus I, 1, 1, and the inverse of that. Now I'm not going to write down what that result is, it's actually quite messy, but one should be able to verify that this is going to be an orthogonal matrix. So that is, every time you have a skew symmetric matrix, the exponential of it will always produce an orthogonal matrix, and if you have a symmetric matrix and you exponentiate that, you will also get a symmetric matrix. I invite you to try and prove those things for the arbitrary case, but we'll just leave them as an exercise for now. So up to this point, we're able to do a squared, a to the power of 53, a to the power of 576, and even exponentials of matrices but up to diagonalization. What if we have interest in finding, for example, the square root or the cube root of matrices, which is 1/2 and powers of 1/3? So what would the square root of a matrix be equal to? So for example, let's assume somebody says, okay, what's the square root of the matrix 1, 4, 9, 16? One proposal is, okay, well, maybe I can just take the square roots of the individual entries, for example, 1, 2, 3, and 4. Well, if that is the case, then what do you think 1, 2, 3, 4 squared should be equal to? Because if it were to have the same properties as square roots, then 1, 2, 3, 4 squared should be equal to 1, 4, 9, 16. But we can actually find that this is going to be equal to 7, 10, 15, and 22, which is not the same thing as the matrix 1, 4, 9, and 16. Therefore, this definition of the square root of a matrix is not at all useful. Right? So if we were to extend what we were talking about before, and for example, consider the eigenvalue decomposition under the assumption that it has one, then we can say that the square root of a can be defined, or is equivalent to, for example, a to the 1/2, is actually equal to u d 1/2 u inverse. And one can say, well, we still need to find what d to the 1/2 is. Well, by properties of closures of multiplication of diagonal matrices, we know that the square root of a, 0, 0, square root of b, times the square root of a, 0, 0, square root of b, is actually equal to a, 0, 0, b. So defining this as the square root of the diagonal entries is actually okay, because we're working with diagonal matrices, and under multiplication, that is actually a very beautiful thing that we have. So for example, let's assume we have the matrix A, which is going to be 4, minus 2, 0, and minus 9. So the first thing that we would need to do is find the eigenvalue decomposition. So for example, the first eigenvalue we have would be 4, and the second eigenvalue that one can find is going to be equal to 9, and then we need eigenvectors associated to each of those eigenvalues. So for v1 we can have 1, 0, and for v2 we can have 2 and 13. So that means the eigenvalue decomposition for A is going to be equal to 1, 0, 2, 13, 4, 0, 0 minus 9, 1, 2, 0, 13, and the inverse of that matrix. So if somebody were to ask you, what is the square root of this matrix A? 4 minus 2, 0 minus 9. We already know that taking the square roots of each of these individual entries is not a good way to go unless this is a diagonal matrix. So from the principles that we've already derived, that would just be equal to 1, 2, 0, 13. So it's going to have the same exact eigenvalues, eigenvectors. And then we can take the square roots of the eigenvalues. So we're going to have 2, 0, 0, 3i. And then the inverse of the matrix 1, 2, 0, 13. Right? And once you multiply that matrix out, you're going to have the matrix 2 minus 4 thirteenths plus 6 thirteenths I. So that's one entry. 0, and 3i. So it's not the most beautiful matrix, but it is the correct one. So I invite you to try and multiply that matrix by itself and showing that it is actually equal to 4 minus 2, 0 minus 9. So that is one application of eigenvalues and eigenvectors and eigenvalue decompositions to find any power, including non-natural number powers of matrices. And you can also apply this to, for example, the inverses of matrices as well, or even powers of inverses of matrices, in addition to the exponential of matrices. Now, a couple of the things that I invite you to explore. How would you define, for example, the sine of a matrix or the cosine of a matrix? If you know the Taylor series of sine or cosine or the exponential representations of sine and cosine, you can use those to your advantage. And just for fun, you may even want to consider, what about the natural log of a matrix? Right? So those are just some things for you to consider for now. But until then, I hope you enjoyed this video. See you in the next one.